Lesson 3, Rotations and Tessellations. So we're going to rotate the square 90, 180, 270, and 360. We're going to do it in a clockwise. Wow, that looks like the word clockwise. So we're going to just imagine this point. If I rotate it 90 degrees, it's now going to be over here. Oh, yikes. So my new shape would look like this. That's a 90-degree rotation. If I wanted to go 180, it would take it all the way over here. So that would be 180. And if I wanted to go 270, it would take it all the way to up here. And 360 would obviously take it back where it started. Okay, tessellations is where we're going to start. So the word tessellate means a pattern created by repeating a shape to cover a plane without any gaps or overlaps. And this has a lot to do with geometry and angles and how many degrees things can be used to overlap. And tile kind of is what we're looking at. So if we go back to this, if this was a tiled shape, they fit perfectly because it makes a full 360 degrees. And that's kind of what we're looking for, is a 360 degrees. So this is by an artist named M.C. Escher. He was a famous artist and mathematician, and he was able to create phenomenal pieces of artwork because he was a mathematician. He has like a lot of optical illusions and things with reflections and refractions and stuff with light, and he did a lot of spherical drawings, all because he had a concept of both what he sees and perceives, but also mathematically how that would translate on paper. So this is two types of tessellations. This one is based off a triangular shape. So you can kind of see the triangle here. That's not a good color. There's a triangle, a triangle, a triangle, a triangle, a triangle, triangle, so many triangles. So it's based off a triangular shape. This one I think is based off of probably a square, and it's got pieces removed and moved around. So what a tessellation is you take one portion of something and you move it to the other. And I'm going to explain that better. So if I take this shape of a square and I want to create a tessellation of it, if I wanted to subtract this side from here, I would have to add it. Oops, it was pretty good up until the end there. On there. So I could cut it from this side and move it to that side. And then they would kind of fit together like a puzzle piece. If I went like this, I'd have to move it down here. If I went like this, I'd have to move it up here, and so on and so forth. So that's how tessellations are created. You start with an original shape. Oh, I thought that was not the eraser. You start with an original shape and then you add and subtract to it. So this could be a shape that tessellates because I haven't actually gotten rid of any of the area of that image. Obviously that looks like crap and it doesn't look like anything. So when Escher did it, he made them look like things, and that is impressive. Mostly I can make it look like a fish. I could probably make one that looks like this with a fish. But that is about it. But he gets more impressive. So this is my favorite of his tessellations. So it seems pretty simple, but what you can notice is that down here, the negative space, we don't really look at it, but as we travel up here, the negative space actually becomes this bird, and you can still see the fish in the negative space here. So he flip-flops the negative space and the positive space by changing the background colors on both of these. So down here, the negative space is the black, and you focus on the white, which is the fish, and then up here, the negative space is the white, so you focus on the black. So it's just really impressive, and the artist in me is happy to have shared that with you because I don't get to talk about art very often in math. Okay, back to the math. We have this formula right here, and it's going to help us decide if things can tessellate. So n is the number of sides. So we're going to just plug this in. So we have 180 times 3 minus 2 over 3, and we get 90 degrees. What that means, also, this is important to note that it's a regular polygon, which means that all sides are the same. So that means that a regular triangle, so that would be an equilateral triangle. I wrote 90, but this is supposed to say 60. Each angle on the inside is equal to 60 degrees. That's all that means. Square is a four-sided shape with four sides the same. If we plug it in, you should know what each angle is because we do this often. And if you said 90, you were awesome. Okay, a pentagon is a five-sided shape. They look like this. I'm going to get not as good at drawing these shapes as we continue on. So 180, 5 minus 2 divided by 5. Type this into your calculator, you should get 108. So that means that each of these angles is 108. Okay, I want you to pause the video and I want you to figure out the hexagon, heptagon, and octagon, knowing that a hexagon has 6 sides, a heptagon has 7 sides, and an octagon has 8 sides. Okay, you should have got 180, 6 minus 2 divided by 6 to get 120. You should have got 180, 7 minus 2 divided by 7 to get 129. And then you should have got 180, 8 minus 2 divided by 8 to get 135. Okay, now we're going to see if it tessellates. So what we're trying to see is if these numbers will go on to 360. So if I take 360 and divide it by 60, I get 6 on the dot. So yes, it will tessellate. If I take 360 and divide it by 90, it gets 4. So yes, it will tessellate. We saw that in this one. It tessellates 1, 2, 3, 4 times. This is going to be a no. 108's not going to go into it. You get a decimal. 120 it's a yes. It goes 3 times. This is going to be a no, and this is going to be a no. So they won't tessellate. So the degrees you have to rotate. Oh, I already answered some of these questions. Okay, so how many of each shape is going to be 6? It rotates 60 degrees. This one rotates 90 degrees, and there's 4 shapes. And this one rotates 120 degrees. So there are 3 shapes. For all the other ones, we got decimals. This one got 3.33. This one got 2.8 and 2.7. Okay, we have 8 semi-regular tessellations. So what that means is that they tessellate, but not just by themselves. So we have 3, 3, 3, 4, 4. So that's 3 triangles. 1, 2, 3, and then 2 squares. We have a 3, a 3, 3, 3, a 4, a 3, and then a 4. We got a 3, a 4, a 6. These are not my strength. The 6 is 1, 2, 3, 4, 5, 6. There we go. And then another 4. We got a 3. And we got a 6. Uh-oh. Okay, wait. I'm going to move this over. We got a 3. And then we've got a 6. And then we got a 3. And then we've got a 6. There we go. That looks good. Alright, a 4, an 8, and an 8. Okay, we're getting harder here. A 4, an 8, 1, and then an 8. 8, okay, This is a very common pattern for tiles on like bathroom floors. Okay, 4, a 6, and a 12. Okay, I am not going to be able to draw that. A 4, a 6, and then a 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Mm-hmm. Yep. Mm-hmm. 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 Cool, cool, cool. No, I'm not going to draw the 12s. That's way too hard. We can do a 3, a 3, a 3, a 3, and a 6. This sounds ridiculous. A 3, a 3, a 3, a 3, and a 6. And then we got a 3 and a 12 and a 12. Basically, it's like a 12 and a 12 and a 3, because 12s are getting so wide that it almost looks like a circle. Basically, the more sides it has, the more it looks like a circle life. Anyways, those are called semi-regular tessellations. We use these a lot when we're tiling things and making things fit on patterns on grounds. Or the very common tile of a 4, a 4, a 4, and a 4. I'm sure everyone has that somewhere in their house, or possibly rectangles, you know, with hardwood. I'm just scribbling now. Okay, where's the picture? There it is. Okay, we're going to rotate it 90 degrees, 180 degrees, 270, and then we're going to see what happens. So let's first find all of the intersections. So this point right here is at 1 and 0. This point is at, just kidding, we don't need that point. Let's start on the left side. Let's start here. So we got -1 and 4, and then we have this point right here, which is -3 and 6, and then we have this point right here, which is -2 and 7, and then we have this point right here, which is -1 and 8, and then we have it all positive, so 1 and 8, and then 2 and 7, and then I don't know where the rest of these are, 3 and 6, and 1 and 4, because it is a reflection of itself. So that's all of those vertexes. So if I was to rotate it 90 degrees, we're going to go clockwise. This point right here at 1 and 4 will now be at this point right here. We can probably just draw the snowflake by figuring out what it would look like if we rotated it. So my new point, I should have drawn it in gray. My new point over here is, instead of being at 1 and 4, I'm now at 4 and -1. And this point up here, instead of being at -1 and 4, is now at 4 and +1. So I'm not sure if you can see the pattern here, but if I have an X and a Y, what's happening is that when I go into a 90-degree rotation, they are changing positions. So my Y is first, and then our X value is changing signs. So it's the opposite sign. So it's Y and -X. So let's use that logic here. So this point is at -3 and 6. We're going to flip it, and it's going to be at 6 and +3. So let's go to 6 and +3, and it's right there, and that does match where that should be on our snowflake. The next point should be at 7 and +2, which is right here, which again looks proper. Then we have -1 and 8. Oh, I think we gotta go in first. Okay, so it'll be at 8 and +1, which is right here. So that's looking pretty spot on. So 8 and -1, 7 and -2, and 6 and -3. So that is our rotated image. So we should be able to fill in this chart and figure out what all of these formulas are. And then what you can do is you can just write these down and use those as formulas. So let's go 180 degrees. So let's flip this point. Let's do this point again. So instead of being up here, it's going to be down here. Oh no. There we go. Oh my gosh. So it's going to go like this. Oh, I screwed it right up. Okay, so it'll go down now. Oh my gosh. There we go. Should go right there. Okay, so it is going to go down now on both sides. So this point went from being at -1 and 4, and now it's at -1 and -4. And down here it went to +1, -4. So what you should notice in this section is that, and actually this point translates to this point. So this is actually -1, -4, and this one is +1, -4. I'm sorry. So what you should notice is that they don't change position, but they both turn into the opposite of each other. So it becomes -x, -y. So using this logic, we're going to rotate this point. It should be at 3 and -6. So 1, 2, 3, and down to -6. It should be down here. This point should be at 2 and -7. This will be right here. Just kidding. No, that's right. And then it will be at 1 and -8. And then we'll go over, and it will be at -1, -8, -2, -7, -3, -6, and there's the bottom of our snowflake. Our last one is the 270. So if it's going to go this way. 1, 2, 3, 4. 1, 2, 3, 4. So this point is going to go from here to here. So it's going to change from 1 and 4 to -4 and -1. And this point right here goes all the way around, and it goes from being -1 and 4 to being -4 and +1. So what you should notice is that your x and your y values are changing location. So it's our y value here, and it is also changing signs. So it's -y, -x. So that's what we're trying to find here. So we're going to flip it. So it's going to be -6 and +3. So -6, +3, which is right there. -7, +2, -8, +1. So there's that side of the snowflake, and then we have -8, -1, -7, -2, -6, -3. So there's our rotated snowflake. So you probably could have just done that on your own just by looking at it, but doing it with the points is a lot easier when you're dealing with just abstract things. So I'm going to write those down one more time. So if you have a point with a 0-degree rotation, it's x and y. If it's a 90-degree rotation, it's going to be y, then -x. If it's a 180-degree rotation, it's negative x, negative y, and if it's a 270-degree rotation, it's negative y, negative x. So save this for your notes. You can write it on your cheat sheet for your test or your final. You can bring it into the test too. Okay, bye.